Welcome to the chapter on synchronization. So in this chapter we'll talk about clocks. So we'll talk about logical and physical clocks because DHTs are not the only things that can be built using distributed systems and distributed algorithms. So for all other kinds of algorithms which we shall see in the second part of this course, we will see that there is a need for different kinds of clocking mechanisms, right, to maintain time. So we can either have physical time or we can have what is called logical time. In a distributed algorithm, logical time is clearly more important, but physical time is also used. So we will see when what is used. So we'll discuss what is called a synchronous system. This relies on physical clocks, or it relies on systems where there is some notion of timing. And then we will discuss asynchronous systems that do not rely on any notion of timing. So it basically means that the delay of a message can be very large, right? So whether it is finite or infinite, that again is a theoretical issue. But essentially you cannot assume anything about the time it takes to process a message or send a message, right? Or the message transmission time, that cannot be assumed. So we'll discuss physical clocks first. So we'll understand the way that the physical clocks work in our watches and within computers. So inside a computer also there is a clock. So the basic idea is the same. So the idea is that a quartz crystal is used to generate a clock signal. What is quartz? Quartz is a piezoelectric material which generates a voltage when subjected to mechanical stress, and when it is subjected to a voltage stress, when you change the potential across it, then also mechanical stress develops on it, vice versa. So the basic quartz oscillator that you have over here, the basic oscillator can be represented with an equivalent circuit which is shown over here. And every quartz oscillator has a natural frequency, right? A natural frequency of oscillation, which is essentially the resonant frequency of this circuit. So basically what happens is that there is a feedback mechanism. Via the feedback mechanism, every quartz oscillator would oscillate at a certain frequency, which for it is the natural frequency. So what happens, as I just showed, that there is a quartz oscillator that is part of a self-feedback loop, and there is of course an amplifier here to amplify the signal to properly embellish the signal. So the quartz oscillator here typically oscillates at 32 kilohertz. So that is the base frequency of the oscillator. Furthermore, this clock can be divided using a standard clock divider circuit, and that can be used to create a much higher frequency. So essentially this can be thought of as the time base, and then this time base can be used to construct a clock with a much higher frequency. The clock drift is very little. It is plus or minus 15 seconds per month, which is fine. So most of our watches don't maintain time to that extent, and the clock drift per se is not an issue. It's only 6 parts per million. But nowadays, of course, quartz technology has improved by leaps and bounds, so it's getting much better by the day. But nevertheless, for large distributed systems, a regular quartz clock is not suitable, because even the 6 ppm error might be on the higher side. So you would want a lower error. So we use a cesium-133 atom as an oscillator. So this is very accurate. So this also uses a similar feedback mechanism, feedback-based circuit as the basic quartz clock. Its accuracy is 10 raised to power minus 8 ppm, 10 to the power minus 8 parts per million, which means it's extremely accurate, extremely accurate. And this is used, and this is what is typically there in what is called an atomic clock. So now let's see that how the atomic clock is actually used. So we'll come to the use of the GPS system. So what happens is that let's consider what is called satellite GPS. So what we actually use in our mobile phones is what is called AGPS or assisted GPS, which means it triangulates based on the positions of multiple mobile towers. That is not exactly what we are looking at. We are talking about regular satellite GPS. So let us consider a simple version of the problem where there are 4 unknowns. So one unknown, of course, is the current time. So we don't know the current time very accurately. Even a mobile phone doesn't know because it doesn't have an atomic clock. And of course, it's x, y, and z coordinates, right? So given the fact that there are 3 unknowns here and 1 unknown over here, a total of 4 unknowns, we would need 4 equations. And the 4 equations will come when we have 4 independent sets of data. And these 4 sets of data would require 4 satellites. So this is basically required for satellite GPS. And this is how time is obtained via an atomic clock. So the basic physics is very simple. It is simply based on the propagation of light and the Euclidean geometry. So of course there are some relativistic effects that also do come into this, and that is of course required, but I'm talking of a much simpler formulation. So if the current position is xyz relative to some reference, relative to some inertial reference frame, the drift between, let's say, the receiver clock and atomic clocks is d. So we are assuming that all the atomic clocks on the satellites, there is no drift between them, but there is some drift between the clock of the receiver, which in this case is the mobile phone, and the atomic clocks. So let's say the time at which the receiver receives the message, let it be tr. So we can set up a small equation, alright. So the small equation that we will set up over here is basically, this is the distance, which as you can see, this is just simple Euclidean distance, where xi, yi and zi are basically the coordinates in this case of the satellite. So tr minus ti is the time that we are reporting. So what happens is that whenever the satellite sends a message, it affixes its timestamp along with the message, and when the GPS receiver receives the message, it looks at the current time. So it then subtracts them, it's tr minus ti. And so this is roughly the time it took for the signal to come from the satellite to the receiver. But of course, since there is a drift in this, we add that. So this becomes the time. So the drift in this case is an unknown. We don't know that. And so if you look at the previous slide, we were assuming that the exact time is an unknown, but this has been changed to make drift the unknown. Mathematically, they are the same thing, just a rearrangement of terms. So given the fact that this is actually the time of propagation, we multiply that with the speed of light. And then after multiplying that with the speed of light, what do we get? So we have distance on the right hand side and distance on the left hand side. So we have an equation in front of us. This equation has 4 unknowns. So what are the 4 unknowns? The 4 unknowns over here are x, y, z. X, y, z in this case are the position of the receiver, the x, y and z coordinates, and of course the drift, right? So which is the drift in time. xi, yi and zi is essentially the position of the ith satellite, and ti is its time, which has been affixed with the message. And given that all the satellites have an atomic clock, we are assuming that there is no drift between them. Now given that we have 4 unknowns, we need 4 equations. So since we have 4 satellites, each satellite contributes an equation of this type. So 4 equations that are quickly solved. So given that we have 4 satellites, let me go back. What we need to do is we just set up these 4 equations, and then all that your GPS receiver does is that it solves these 4 equations. There are many techniques on how to solve them. I'm not getting into that, but let's put it this way, it's easy to solve. And once it is solved, we can also find the drift, meaning we can find the exact time, right? We can compensate for the drift and find the exact time on the receiver, as well as we can find its coordinate x, y and z. So normally we don't use the z coordinate, so we can make a fixed assumption. If we know what is the elevation of a certain region, then of course we can just have x, y and the drift. So then we would need 3 satellites, which is most of the time done incidentally. Or if we really want the z coordinate, let's say for an aircraft or something, we would need 4 satellites. So this is of course a very exact mechanism of doing it. But let's say that when the z coordinate is not an issue, what we would need is that we would need to triangulate. Alright. So then let's say that if this is not an unknown, we would need 3 satellites or 3 other places that can give us the exact time. So normally what we have in assisted GPS is that we triangulate. So when we triangulate, what we actually get is that we find the distance from 3 mobile phone towers, and that gives us an estimate of the current location. So this is normally what we refer to as GPS, and this, as you can see, is much cheaper than actually getting the coordinates from the satellite. And since most mobile phones are in a region with a signal, this is often easy to do. It's easy to achieve. Alright. Now let us consider a slightly different protocol. So in this protocol, what happens is that there is no external time base, like there is no satellite or there is no mobile phone tower. There are just a set of machines, and they want to ensure that between themselves they have a synchronized time. Alright. So given that there is no external provider, they will have to somehow ensure that all of them are following the same time base. And this time base might not match with the real wall clock time, but that is okay. Insofar as running a distributed algorithm is concerned, as long as all of them refer to the same time, it is okay, right? Use the same time base, it is alright. So this is where we use the network time protocol. You would have heard about this in many scenarios. So this is called NTP normally. So what happens is that we have a set of network time servers that have accurate clocks. So let's call it the stratum 1. These servers synchronize themselves with an even more accurate clocks, which are mostly atomic clocks, which are stratum 0. But these atomic clocks are typically not accessible to common users like us. So we would basically synchronize our times. If you go to the Windows time setting or Linux's time setting, it will give you an option to synchronize the time with a network time server. And so these network time servers are run by numerous agencies, and most universities also run them, major vendors also run them, doesn't matter, they're all in stratum 1. All that my machine needs to do is it needs to connect to a network time server and synchronize the time with it. Mobile phones also do that. You would have often seen that, let's say you take a flight and land up in a region with a different time zone, or let's say your mobile phone is off, you charge it on the plane, and then when you land, what you would actually see is that the moment it gets its signal, the time changes. The time changes mainly because it synchronizes the time with the clock of the tower. So this is a stratum 1 synchronization. And client machines contact the NTP time servers, find the drift between the clocks and update their clock. So this is of course a simple example, but we'll look at slightly more complicated examples where we discuss advanced forms of clock synchronization. So what happens is that we will discuss the simplest algorithm first. It's called the Christian's algorithm. So here the client sends a request to the server at its local time t1. Alright, so let's consider the client and the server. So it sends a request at its local time t1. The server receives it. Sorry, I should put t1 over here, not here. And the server receives it at time t2, which is its local time. Server then sends a reply at its local time t3, which the client receives the reply at t4. So if we assume that the jitter in the network is 0, which means that it took the same time to send the message from the client to the server, and it took exactly the same time for the reply to come back. If we assume that this jitter is 0, then the request and response take the same amount of time. What do we have? What we have is T2 minus T1 plus delta. So let's say that when the time was T1 at the client, the actual time was T1 plus delta with respect to the server, right? So the delta here is the drift. So this is the time, this is essentially the message transmission time, right? So let's call it T trans. Similarly, when the client received the message, it received the message at T4, which is the client's local time. So the server's local time would be T4 plus delta, where delta is the drift between the clocks. And this minus T3, where T3 is the time at which the server sent relative to its own clock. So this is the transmission time again, T trans. And given the fact that we are assuming that there is no jitter in the network, which means it takes the same time to send and same time to receive, we have an equation over here, and the value of delta can very easily be computed as T2 minus T1 plus T3 minus T4 divided by 2, which is just a simple algebraic reduction from here. What this essentially teaches us is that if we just consider the client, a client and a server, regardless of any external time base, it is possible for the client to figure out the clock drift between its clock and the server's clock, and then the client can adjust its local time such that the drift becomes equal to 0. So in this case, even in isolation, a client and a server can synchronize their clocks using this simple algorithm, which is called the Christian's algorithm. Of course, the key assumption that is being made over here is that the jitter is 0, which means that the message transmission time, regardless of the sender or receiver, as long as the link is the same, remains the same, regardless of the direction. So then at the end, what happens? The client shifts the clock by delta, and that sets their clocks to be the same. Now we'll discuss the Berkeley algorithm. So the Berkeley algorithm is an extension over and above the Christian's algorithm. So in this case, a master is chosen by some method among a group of nodes. So let's say we have a group of nodes. One among them is chosen as the master. So the algorithm calls it master, but let's call it a leader. So they choose a leader. Well, how will they choose a leader? Remember this, we will discuss leader election algorithms maybe 1 or 2 lectures later. But let's assume that there is some way for the nodes to select a leader, which is one distinguished node among them. Let's not look at failures for the time being. The leader / master will use the Christian's algorithm that we just studied to find the clock drift with each slave. So what does the leader do? It basically finds the clock drift with each slave. Right? We call them master and slave over here, not leader and follower. Then what the master does is that it computes the mean value of the drift. Alright. So master then sends an update to each slave regarding the amount that the slave needs to shift its clock. So what this basically means is that once, let's say, you compute all the drifts, you compute the mean, right? The mean of the drifts. So then let's say this value be delta m. So then what happens is that all the nodes assume that they would like to synchronize to a clock which is delta m shifted from the master. So the master will make an appropriate calculation and send the amounts that they need to shift their clock by to each of the slaves, including itself. All the slaves, including the master, will shift their clock. So this will ensure that the clocks of most slaves and the master are relatively synchronized with each other. Furthermore, given the fact that we consider the mean, this will minimize the amount by which each slave needs to adjust its clock. So basically major adjustments are avoided. Let me summarize this algorithm in a different manner. what will happen is that if we have the master and we have a set of slave nodes, different slave nodes will have different values of the drift. One option could be that we say that, look, the master's clock is correct. All the slaves, look, this is your drift. You correct your clocks such that you are totally in sync with the master. The other is that we say that, look, none of the clocks are correct. Let us instead find the mean value of the drift. Then let us assume that the correct value of the clock is essentially T master, which is the current T master, plus the mean value of the drift. Let this be the correct value of the clock. Given the fact that we know that this is the correct value, the master as well as the slaves need to change their clocks such that all of their clocks are roughly synchronized to this hypothetical value, and furthermore, the amounts that they need to actually change their clock is not much, because the fluctuations across the mean are not expected to be great, are not expected to be substantial. So this is like a higher level algorithm over the Christian's algorithm that uses the Christian's algorithm as one of its components to find the drift between each pair, each master-slave pair. So now that we have discussed these physical clocks, it is time to discuss a small algorithm with physical clocks or synchronous clocks. We'll call it totally ordered multicast. So what does this mean? What this means is that if there are a set of nodes, and let's say one node is sending a message to a subset of the other nodes. Let's say this is sending this message and this is sending this. The other node 1 is sending these messages, node 2 is sending these messages. So then the order in which the messages are received should be the same across all the nodes. In the sense, it should never be the case that message A from, let's say, node 1 was received before message B in one of these nodes, and the other node records a different order, which means message B was received first and message A was received later. That should not happen. So sending to multiple nodes is called multicast, but ensuring that there is an order for every message is known as total ordering, right? So the algorithm here that we are discussing is totally ordered multicast. So the problem is as follows. So the problem is that we have a system with multiple nodes. They randomly send messages to a subset of other nodes. So it is important to note that they are not sending a message to a single node, but they are sending a message to a subset of other nodes. Furthermore, the network has a non-deterministic delay. However, the delay is bounded by capital delta, and we need to ensure. So there is also one more assumption that we are making, which I am not stating because it has kind of been flowing from the last few slides, which is that we are assuming that their clocks are synchronized. In such a scenario, we want to ensure that all the messages are delivered in the same order at all nodes. So as we have just discussed, it should never be the case that, let's say, node A says that message A was delivered before message B, and let me explain that once again. It should never be the case that node A says that message X was delivered before message Y, and node B says that message Y was delivered before message X. So this should never be the case. Alright. So this is not totally ordered, but let's say if all of them see the same order of delivery, it will become totally ordered. So what we do is that we timestamp every message with the local time. So here, of course, the assumption is that the local time is clock synchronized. For the receiver, for a message with timestamp t, all that it does is that it transfers it to the receive queue at time t plus delta. So why t plus delta? Well, the answer is very simple. So we are assuming that the network has a non-deterministic delay. this is bounded by delta, or alternatively we can say that the network has a fixed delay but the clocks are not fully synchronized, they have a skew of delta. So we can play it in different ways, but the important point is that if, let's say, I am receiving the message, or let's say I am sending the message at time t, okay, so every message is being time stamped, and let's say the sender is sending the message to a multitude of receivers, it is transmitting the message with its own timestamp, which is t. So let me show this in a better way. If this is the sender, it is sending the message to a bunch of receivers. The message has a timestamp which is the sender's time, which is t. So let us for the time being assume that all the clocks are synchronized. The only jitter is there in the network. Subsequently, at a later point of time, the receiver receives the message. So if, let's say, it waits for all messages, okay, as you can see over here, that if, let's say, it waits for all messages till the time t plus delta, alright. So this will essentially guarantee that all messages sent before time t have reached it, right? So what am I saying? What I'm saying is that at time t plus delta, the message is transferred to the receive queue. The property that I am claiming that all messages sent before have been received. Correct? Not only have they been received, they have also been put in the receiving queue. That's exactly what I'm saying. So why am I saying that? Well, the reason I'm saying is that, let's say, consider another message that was sent at time t dash. So let's make a simplistic assumption. If you want, I can break it later, where let's assume that the network transmission delay, the minimum delay is 0 and the maximum is delta. So in this case, what would happen is that, let's say, I transmit another message at time t dash, and this is just before t. That's okay. So after delta time units, which is the maximum, this message would have been received by all the receivers, and this would automatically guarantee that because of this maximum time, which is delta, any message sent before it would also have been received. And then, so this is why when we add this message with time t to the receive queue at time t plus delta, we are sure that all messages sent to the current receiver with a timestamp less than t are present in the receive queue. Alright, so that is important. This property that all messages sent before t to the current receiver have been received and also have been placed in the receive queue. This is important, and this is directly a consequence of two things. One is clock synchrony, and the other is bounded network delay. Alright, so it's a consequence of these two properties that this is happening. So given that we have this, what we can see is subsequently we deliver the messages in the receive queue based on the order of the timestamps. So what we do is we take a look at the receive queue, and given the fact that every message is timestamped with a timestamp, we deliver the messages from the receive queue to the process. So this is not a first come first serve queue, but it's rather a priority queue. And the priority in this case is the timestamp. So based on the order of the timestamps, they are delivered to the receiver process. So the claim is that this is a totally ordered multicast. So we will see why. So the key idea is that let's go to the next, let's just clean this up. So the key idea is that if you consider the receive queue, right, and if you just take a look at the timestamps, what we are saying is that you take the minimum timestamp over here and let this minimum be, let's say, tmin, and you deliver this message to the receiving process. So let us assume that this is wrong in the sense that there is one more message which should be delivered, and this message has a lower timestamp, right? It has an earlier timestamp, but that is not possible given the fact that we just proved in the previous sheet that all the messages with a lower timestamp are already present in the receive queue. So it will never be the case that any message with a lower timestamp will not be present in the receive queue. So let me write that all messages with a, let's call it a smaller timestamp, are already present in the receive queue. Okay. So given that we have this property, we will essentially be delivering messages to the process in an ascending order of timestamps. So this is clearly globally ordered because we are clearly not missing any message. So we are not dropping any message, right? We are waiting for the message to come. Not only the message to come, all of its predecessors to come because of the delta property. So we are not missing a message. Okay, this is not happening. Given the fact that we are not missing a message, we are looking at all the relevant messages that should be considered, and we are delivering in exactly the same order, which is the order across nodes, which is exactly the same order across nodes, which is essentially the order of increasing timestamps. All right. So we are delivering in exactly the same order. Hence, given these two properties that no message is being missed and we are delivering in exactly the same order, which is an ascending order of timestamps, right? This proves that we have achieved a totally ordered multicast. Now the problem is that this did make assumptions on bounded network delay, or let me call it bounded jitter. This did make assumptions about clock synchrony. So these assumptions don't hold in practice for a practical distributed system. The reason being that we can have reasonably large indefinite delays in the network as well, and along with that we don't have clock synchrony, right? So we need to create some method of a logical time and try to achieve the same thing, maybe not multicast, but a slightly simpler problem. And we can of course extend this to multicast and see how to do it with a logical clock. Instead of a physical clock, use a logical clock that does not make these assumptions. So given that we don't want to have a notion of global time, what we can do is that we can think of processes. So every process over a timeline has its own events. So events can either be internal events, or event can be a send and the other process can receive. So it can be a send and a receive, right? So let us define a happens before relationship. If a process issues event A before event B within the same process, then we can clearly say that A has happened before B. If event A is the sending of a message by one process and B is its receiving by another process, then also we can say that look, event A has happened before event B, because it is not possible to receive event B without A being sent, right? So these are our two happens before relationships. One holds within the same process and the other holds across processes. And essentially same process, we keep on incrementing our events, and a send receive, the receive needs to happen after the send. Furthermore, transitivity holds in the sense if A happens before B and B happens before C, we can say that A happens before C. So the transitive property does indeed hold. So we are trying to develop some notion of a logical time which is different from physical time. So now let us look at some definitions. So if it is the case that A has not happened before B and B has not happened before A, so this of course can happen in a distributed system, it can't happen in a physical system, but in a distributed system it can definitely happen. So let's say there are two events on two different processes, and those processes don't send any messages between each other. So then it will be the case that look, A has not happened before B and B has not happened before A. So A and B are said to be concurrent. So we will use this symbol for concurrence. If A happens before B, then we can say that A causally affects B in the sense that there is a causal dependence. A happens first, A is the cause and B is the effect. So let us create what is called a Lamport clock. So let us assign a number to each event. So let's say for event A, let us assign a number to it and let's call it the Lamport clock. It's an integer number. It's a natural number. So we wanted to satisfy some conditions, the clock condition that if A happens before B, tau A, the time of A, is less than the time of B. So the clock condition can kind of be broken into two sub conditions, that if A happens before B and A and B belong to the same process, then obviously tau A will be less than tau B, right? So we need to ensure that. Second, if A represents a send and B is its receipt, then also we need to ensure that the timestamp of the sender is less than the timestamp of the receiver. So these are the two things we need to ensure, C1 and C2. So the enforcing the clock condition is easy, it's not hard at all. Every process keeps a clock which is a counter that is initialized to 0. So let us call process i's clock or process i's counter as tau I, Ti. So then, let's refer to tau I as Ti. I'll not use the term tau anymore, I'll call it Ti. Each process increments Ti between two successive events, right? So this ensures the clock condition C1 that whenever I have one event and then I have one event after this, if this is Ti, I just increment it by 1. If event A is the sending of an event, is the sending of a message, sorry. If event A is the sending of a message, let me just change that by process I, then this process embeds its own timestamp in the message, right? So what it does is that it embeds its timestamp in the message, and let B be the receive event at process J. Okay. So what we will do is we need to ensure that the timestamp of B is greater than the timestamp of A. And A is the send event and B is the receive event. So what we do is that we compute a max operation between this timestamp, which is A's timestamp, and B's existing timestamp. So clearly, the final timestamp of B has to be greater than both, which is its existing timestamp as well as the timestamp of A, right? Because it's a new event. So this needs to be the case. So we compute a maximum of them and then we add 1 because it's a fresh event. So 1 of course comes because it's a fresh event, but the maximum comes because number 1, we don't want to go back in time. So given the fact that we don't want to go back in time, the timestamp of B will only increase. But the other thing is that if A has a higher timestamp, so let's say if A's timestamp is 10 and B's is 5, we first need to compute the maximum of 5 and 10, which of course is 10, and then add 1 because it's a fresh event. So this becomes 11, and 11 becomes the timestamp of event B as well as the timestamp of process J, right, as well as the current time of process J. So this method, which is very simple, essentially the two clock conditions C1 and C2, the way that they are being enforced is extremely simple. So for C1, what we are doing is that any new event of a process, we are just incrementing the counter by 1. And for C2, what we are doing is anytime A sends a message, anytime A is the send event and B is the receive event, we just ensure that the timestamp of the receiving process is greater than its current timestamp and the timestamp of the sending process, and we add 1 because it's a new event. So this does provide a partial ordering between the events, but it does hold both of our clock conditions C1 and C2, and this is called a Lamport clock, a simple Lamport clock. So it's called a scalar clock. It's a Lamport scalar clock. Okay. So what we have seen is that if A implies B, it implies that the time of A is less than the time of B. What about the converse? If the time of A is less than the time of B, does it imply that A happened before B? If this were the case, okay, bear in mind, then if A and B are concurrent events, it would imply that their timestamps are the same. So A and B are concurrent basically means that A does not happen before B, B does not happen before A. Given the fact that both of these relationships hold, you will clearly see that if A hasn't happened before B, which this basically means that the timestamp of B is not greater than the timestamp of A. Similarly, the timestamp of A is not greater than the timestamp of B. Alright, and so then they must be equal. But we will see an example where this actually does not hold. In this case of a scalar clock, this actually does not hold. So consider event A and B in the same process. So what you can see is that event A and event C are concurrent because they are in different processes and there is no send-receive interaction happening between them. Given that they are concurrent, by this assumption, their time should be the same. Again, given that B and C are concurrent, by this assumption the time should be the same, which leads us to the fact that this and this should be the same. This is clearly not the case. There is a contradiction because these are events issued by the same process. So what we find that, so this essentially proves by contradiction that the converse is not true, which means if A happens before B, then it is correct that a scalar clock would ensure that the time of A is less than the time of B. But the converse is not true, which means that if, let's say, this is the case, okay, then it does not imply that A happened before B. This is clearly not the case, because if this were the case, then this would hold. And we are clearly seeing that this relationship for this example is not holding. Given the fact that it is not holding, we can say that in this case the converse is not true. It's not correct. So we can't say that if, let's say, two scalar clocks, one is less than the other, it would automatically imply that there is a cause-effect relationship, a happens before relationship. This cannot be implied. So what we do is that instead of a scalar clock, we have a vector clock. This solves the converse problem for us. So every process I has a vector clock, which is basically a vector of scalars. If there are n processes in the system, then we have n elements in this vector. So within this, the private clock of I is also embedded. It's essentially the ith element. So to ensure condition C1, whenever process I has an internal event that would include a send or a receive, it would first increment. So let us refer to this clock as Vi. It would first increment the ith element. right? On any send, receive or any internal event, it will do that, and then it will send the message, and in this case the message will be timestamped with the vector clock. That is important. That is important to bear in mind, that the message will be timestamped with the vector clock. So what we see here is that if there are n processes, every process maintains an n element array Vi. Process I increments the ith element before sending or receiving a message or any internal event, and every message is timestamped with the vector clock of the sender. Now the sender sends a message to the receiver. So needless to say, before sending, the sender would increment its own private clock. So if it is, the sender's ID is I, it would increment the ith element of its ith clock, and after process J receives, it would first increment the jth element of its clock, which means its own private clock. It will increment within the array, the jth element, it will increment. But here is the key operation. The key operation is, and I'll maybe take you over there. So the key operation here is that, let's say if the sender is sending something to the receiver, it is attaching its vector clock along with it. Subsequently, the receiver is receiving it, it is updating its own internal vector clock, and finally we have a sender's clock and we have a receiver's clock, right? Appropriately, internal values appropriately incremented. So we are looking at two vectors, right? So what we do is that we compare them element by element. For every element pair, something like this, for every element pair, we compute the maximum. This is similar to what we were doing with the scalar clock. We do exactly the same with the vector clock as well, where for every element pair, we compute the maximum, and this maximum is used to compute the final value of the jth process's vector clock. So this is shown mathematically over here, that what we do is that for all elements, we compute the maximum of the of process I's clock and process J's clock, element by element maximum, and we set it to the kth element or the final value of process J's vector clock. Alright. So instead of the maximum of two numbers, we just compute the pairwise maxima across the vectors, similar corresponding elements across the vectors, and the final value of the vector clock is just the result of the maximum. So then how do we say that one vector clock is less than the other? So by the way, before we say that, the internal events, this is ensuring clock condition 1, this is ensuring clock condition 2. We will see why. So we will need to see how, because we have still not talked about how two vector clocks are less than or more, but we are essentially looking at clock condition 2, which is simple, which is straightforward. It follows from the definition of maximum that for all k, if let's say Vi is less than Vj, it means that for all k, Vik is less than equal to Vjk, right? So it means that for all values, it is never the case that any value at any cell is more than the corresponding value in the corresponding cell of Vj, right? That's never the case. It's always less than equal to, but they are not strictly equal. They are not the same, which means there exists some k for which, right? There exists some k for which Vik is less than Vjk, right? So there exists some index for which the kth element Vi, kth element of Vi is less than the kth element of Vj. For the rest, it is less than equal to, but for at least one element, it is strictly less than. Or in other words, I can say that it is less than equal to for all elements, but the clocks are not equal. This would translate to the same thing, which means there is at least one element where they are unequal, and ith element is less than jth. I's element, process I's element is less than process J's element. So this, as you can see, automatically guarantees clock condition C2, because the mere fact that we are computing a maximum will enforce this condition, alright, and the mere fact that we are incrementing the receiver's clock, alright, that would enforce this condition that, so receiver is expected to have the latest version of its own clock, right, of its own counter, and given that that is being incremented, that would automatically enforce this condition, because there is no way that the sender would have the same value for the for the case when k is equal to j. So there is no way that the sender would have the most recent value of this, because the receiver just incremented it just before getting this message. So at least for this element, Vik will less than be Vjk, or let's put it this way, Vij will be less than Vjj, which is exactly what we ensured by the increment. So if you just look, before every send or receive, we increment, and this precisely ensures this condition. So given that our clock conditions are satisfied, this does follow the definition of a logical clock. And now we can say that, let's say if there is a chain of causality, if let's say A happens before B, it can happen before B in two ways. One is they are events in the same process, then automatically by clock condition 1, we have VA less than VB, right? So this is the clock condition 1. If A is a send and B is a receive, we also have VA less than VB by clock condition 2. Now the key question is, let's assume we have this. Does this imply that A happened before B? Well, so it does. So the thing is that it actually does. So the implication is both wise. So the original is true, the clock condition is true, as well as its converse is also true. And the reasons are not hard to actually think about. So let's prove this. So what we need to prove is that VA is less than VB. So there are two events A and B, and then we need to say that there is a path of causality between A and B, right? So that's what we need to prove, because the other direction we have already proven. So for this, of course, if A and B, if there are no events in between, then it is easy to prove, right? So that is a trivial case. So let's consider the harder case where there can be any number of events in between, alright? So let us now consider, so let's say that this is process I and this is process J, right? So let us look for event A, let us look at, so essentially event A was issued by process I. So let us look at the ith component of this. See, of course, if this is 0 means that this is not an event, so it cannot be 0, right? So given the fact that it's an event, it has to be associated with a non-zero timestamp of at least its originating process. So this clearly cannot be 0, alright? But let's say this is some value which is greater than 0. And so let's say that the value of this is equal to x. So given the fact that this property holds for process I at least, which is the originating process of event A, its ith element is for sure greater than or equal to x, right? So now the question is, how did it get to know? The only way that it would have actually gotten to know, so this is a different process, right? So this is process J, and so this is a different process. So how would you ever get to know something about another process? Given the fact that you can only increment your own private timestamp within the vector clock, which is the timestamp corresponding to your own process ID, you cannot increment any other process ID. The only way to get information is if somebody sends it to you. So which basically means that the only way that VB knows that the ID of this, alright, is x or is some value greater than or equal to x, is only possible if, let's say, there is some event in process I where A happened first and then maybe something, there was some complex series of interactions, doesn't matter. but then there was some event that set the value to whatever. So let's say the value of VBI is x dash, so it set it to x dash, and then this value was again communicated, could be via a host of processes, it doesn't matter, but finally it was communicated to process J that look, the value is x dash, and clearly x dash is greater than x, greater than equal to x. So given the fact that x dash was communicated to it, there has to be a causal chain of events within the same process and sends and receives. That is the only way that event B that is happening in process J actually knows about the value of the clock in process I, and in particular its ith component, right? So it at least has the value x which A is recording, or some value which is more than that, which can only be possible if it was explicitly communicated to J, maybe directly or via other processes, it doesn't matter, but nevertheless there has to be a causal chain, otherwise J will simply not ever get to know. And given the fact that J knows that a causal chain does exist, and this does prove that if one vector clock is less than another vector clock, you can establish a causal chain of happens before relationships. So given the fact that we have actually proven both directions, so we have proven that if, let's say, there is a causal chain, the vector clocks one is lower than the other, and if, let's say, VA is less than VB, there is a causal chain between the events A and B. We have proven both directions, so we can have an if and only if kind of implication, right? Implication both sides, means it's equivalent. Now, given that it's a vector clock, so let's say we have two processes. So one vector clock can be 3, 5 and the other can be 5, 3. And this would basically indicate that VA is not less than equal to VB, and VA is also not greater than equal to VB. Okay. So there is no less than equal to relationship and there is no greater than equal to relationship, in the sense that these are not comparable. Given the fact that these are vectors, in a sense, these vector clocks are not comparable. So since the vector clocks are not comparable, in this situation we will say that the events A and B are concurrent. Alright. So this is the definition of concurrence in the world of vector clocks. So what vector clocks have actually given us is that, as opposed to scalar clocks, we just implied that, look, if there is a causal relationship, I can say something about the scalar time of A and the scalar time of B, right? It's less than. Vector clock said that, look, it doesn't matter, you can infer causality, right? You can infer causality from the values of the vector clocks themselves. So if, let's say, one vector clock is less than the other vector clock, you can infer causality, and if there is causality, then of course VA will be less than VB. So it did solve the problem of scalar clocks to a certain extent, but its overheads are more, right? We need to store more and we need to transmit more. Now, given the fact that we have seen scalar clocks as well as vector clocks, let us look at an algorithm that uses the Lamport scalar clocks, and we will call it totally ordered mutual exclusion, which is different from totally ordered multicast, even though there is a total order over here across the processes. So we will solve this using a simpler variant of our clocks, and we will show that in a world with non-deterministic network delays, which can be very large, in a world without clock synchrony also we can achieve a lot just by using our notion of time, which are scalar clocks, and in some cases we will also end up using vector clocks. Alright. But we will still make one key assumption, which is the fact that we have FIFO channels, which means that if a sender is sending data to a receiver, and let's say it is sending two messages, let's call them M1 and M2. If, let's say, M1 was sent first and M2 was sent later, the messages will never get reordered in the network, in the sense that receiver will receive M1 first and M2 next. Alright. And so basically we'll think of these as FIFO, first in first out channels, where the network can delay messages and the delay can be indefinite, but it will never reorder messages. So this FIFO channel assumption we will always make. So let us now look at the mutual exclusion problem. So first we will consider what it means for two events A and B to be totally ordered, right? So we will go back to our definition of Lamport scalar clocks, right? So we'll not consider the vector clock, but we'll consider the scalar clock. So what we have said is that the scalar clock has limitations, but as far as we are concerned, we will try to derive some meaning out of it. So we will say, right, we will say the following. Of course, this is not completely in consonance with the definition of a scalar clock, but here is what we will say. What we will say is that if, let's say, A is a send and B is a receive, then of course the clock conditions will hold, right? And we will further also say that, look, as far as we are concerned, right, the converse is true, even though we know it not to be true, but let's assume, just for the sake of discussion, that we say that, look, we order all the events by their scalar clock time, and if two events have the same scalar clock time, then we order them by the IDs of we break the ties by the IDs of the processes. All right. So this is kind of an alternative definition of a scalar clock, and it does not, technically speaking, we are talking about the converse, and technically speaking it doesn't hold the way we have defined it. But let's assume that we have a Lamport scalar clock, and for the purpose of ordering, right, just for the purpose of ordering events, I repeat, we say that, look, event A appears to be before event B if, let's say, the clock of A is less than the clock of B, right? And furthermore, event A appears to be before B if their clocks are the same but process I is less than process J, right? So this is, by the way, also called lexicographic ordering. So this is like imposing a total order on events when it actually doesn't exist. But let's assume that we do it, and we still use the scalar clock mechanism that we have. So what are we going to do with it? So we will solve the ordered mutual exclusion problem. So mutual exclusion, basically, I'll give you a real world practical example first, and then I will talk about it. So let's say that we have a system where we have a set of nodes. So the nodes can be desktops, laptops, doesn't matter. And then there is a shared printer. So as far as we are concerned, only one of the machines in the network can access the shared printer, and it can print a page. So this is a resource which cannot be acquired by two machines at the same point of time. It cannot be used concurrently. And furthermore, once it is being used, the use has to finish, then only the next use will start. So we can say that different machines will have different usage requests. They will somehow coordinate between themselves to ensure that the property of mutual exclusion, as I just defined it, this holds, in the sense only one request can use the printer at a given point of time, right? It's important that this holds. Furthermore, we will use the mechanism of Lamport scalar clocks to create some protocol where the scalar clocks are incremented the way that we have described, right? So the aim is to create a distributed protocol. We will not assume clock synchrony. So these are the things that we will not assume. We will not assume a bounded network delay. Right? These two things we'll not assume, but of course we'll assume FIFO channels. That's important. Between any two nodes, we'll assume a FIFO channel. So with this in mind, let's go back to our mutual exclusion problem. It says a certain resource can be owned by only one process and it has to be explicitly granted and released. Different requests must be granted in the order in which they were made, which basically means the order by which this total ordering that we have imposed. So this total ordering that we have imposed, different requests are made in that. All right. And right, so they are consistent with this total ordering. And if no process hangs forever after taking the resource, then every request is ultimately granted. In the sense, the protocol is fair. All right. So if I were to consider this, so let us look at the Lamport's algorithm for the mutual exclusion problem. So the mutual exclusion problem is very generic. Okay. So in any distributed system, ultimately, if let's say 10 nodes are going to coordinate and do something, then they will have to, whenever there's a shared resource or they want to, let's say, access something. So mutual exclusion is mainly for access, in the sense they want to access something where only one machine or one process can access at a single point of time. Then of course we need this. And it's a generic mechanism because let's say that you want to run some other algorithm, or let's say you want to centralize the algorithm and you want one machine, one process to kind of take over. Then also such kind of mechanisms are required. So we will discuss mutual exclusion. Then these algorithms will naturally lead us towards what is called leader election, where out of all the processes we can elect a leader and the leader can do something on behalf of the rest. So we are pretty much going in that direction, but as I said, mutual exclusion by itself is a very worthy problem to solve, because in many a time in a distributed environment, we do have shared resources and hence the mutual exclusion property is required. So what is our model? Our model is very simple. The model is that we have n processes, all right, and okay, so the model is that we have n processes with us and we have a single resource that needs to be requested for. So the n processes compete for it, and let's assume that a subset of them are interested. So to request for a resource, this is what needs to be done. To request a resource, pi, process I, sends a message, and the message is tm, I. So what is tm? Tm is essentially the Lamport scalar clock of the ith process, right? So it does whatever incrementing etc. it needs to do, and it sends tm, and also it sends its own process id, which is I, all right? So this tuple over here is what is sent. So this is sent to the rest of the processes. So every process will send this tuple to the rest of the processes, which is n-1 other processes. So when process Pj receives this tuple, so the first thing is that in any communication that involves scalar clocks, it increments, it sees the value and it increments its clock, right? Using the operation that we have seen, which is C2, in the sense it increments its private clock and then it takes a max. Sorry, it takes a max first and then increments. Yeah, sorry. It takes a maximum first. The maximum of the clock of I, max of Tm, and let's say Tm is T message, which is clock of I, and then its own clock, which is J, and then it adds 1, which is what we have seen. And after that, after incrementing its local clock, it just puts the message in its request queue. Furthermore, it sends a timestamped acknowledgement, and the acknowledgement basically says that, look, this is an acknowledgement, it's coming from process J, and this is the internal time of process J, which has been incremented after receiving the message. All right. So you receive the message as per your Lamport clock, you take a max and increment, and you send a timestamped acknowledgement. So this is the first round of the algorithm where a message is sent to n-1 other nodes. All right. Now to access the resource, what needs to be done is that we will access the resource when these two conditions are met. Okay, so what we will do is that when this message is the earliest message in the queue, so the earliest by the time, in the sense that we look at all the messages in the queue, and so who looks at it? The ith process looks at all of the messages in its request queue. And let's say TMI is the earliest, which means either TM is the lowest timestamp, or if there are other ties for the lowest timestamp, then it will break the tie by the process ID, and if I is the smallest, then it becomes the earliest message in the queue. So this is condition 1. Condition 2 is that the process has received a message with timestamp greater than TM from every other process. So every other process has basically sent a reply to I. So it could be another message as well from every other process. So every other process has basically sent it a message with a timestamp which is greater than the timestamp of the message, which is TM. See, if both of these conditions hold, then we claim that it is safe to access the resource. Then what is the protocol for release? Well, the protocol for release is that after the resource has been accessed, then what happens is that PI scans its own request queue, removes the TMI, the message that it sent, because recall that it sends a message to everybody on the network n-1 nodes, and also adds the message to its own request queue. So this own message over here is removed. Furthermore, it sends a timestamped release message to all the other processes, to the rest of the processes. It sends a release message which basically says that I am releasing my current claim, so this request henceforth stands released. So when process Pj receives a release message from process I, it removes any request from process I in its request queue. So this basically ensures that the original message that it had sent to, let's say, process J, which was TMI, so this message, once the release message is sent, the message is removed. So the protocol is very simple. The protocol as such is not hard. So let us go back and discuss this protocol for a second. So the protocol as it sounds is very simple. We have, let's say, process I. If it wants to request, then it sends a timestamped message. So let's say it is its own personal timestamp TII. But given that TI represents, we can use the term TM for the message. So it sends it to everybody, the rest of the nodes. Along with that, it adds the message to its own request queue over here, right? And so these are n-1 messages. Subsequently, each of them, they increment their internal Lamport clock and they send a reply back. So this is a second round where again n-1 messages are sent, which are all the acknowledgements, right? All the acts. Subsequently, what happens is process I scans its request queue, all right. So after scanning its request queue, here is what it does. So it takes a look at all of the messages that are there in its request queue. So it just keeps on doing that. So within its queue, it tracks the message that it had sent for getting access to the resource. The moment this becomes the earliest message means this is the one with the least timestamp. And if there are multiple messages with the same TM timestamp, I will be the smallest. So that is the way we break ties. So it waits for the time when this becomes the one with the least timestamp. So this is condition 1. And second is it should have received a reply, right, from every other node, right, from the rest of the n-1 nodes. As you can see over here, it would have received a reply, a message with a timestamp greater than tm from every other process. So every other process would have sent it a message greater than tm, all right, and so once we can say that every other process sent a message with timestamp greater than tm, right? So it's not greater than equal to, it's greater than tm. Once both these conditions hold, we claim that it is safe to access the resource. And we also claim that concurrent accesses to the resource are not possible, right? So this is the claim that we are making. Once this is done, nothing much needs to be done. You just throw out that original message from here, and then again send another message called a release message, right? So the phase 3 is that I again sends a release message to all the nodes saying that, look, you kindly remove the message that I had sent, which was TMI, from your internal queues. So from your internal request queue, you will have the TMI message, you kindly remove that. So this is again n-1 messages. So as I had said, in a distributed algorithm, the complexity is measured by the number of messages that are sent. The reason being that internal computations are very fast and network messages are expensive. So the total number of messages we need to send are 3 times n-1. Let's say approximately 3n, for large n of course. So hopefully the protocol is clear now to all of you. The important thing is, why does it work, right? So the proof is interesting, right? So that's the important thing. Why does it work, right? So we will discuss the proof shortly. So we'll first discuss the main idea, then I'll take you into the details. So the main idea is, if the resource is free, so let's say nobody else is accessing it, then immediately everybody will get the request, they will send an acknowledgement, and then the original process will immediately start accessing the resource, right? So that is clear. What we are claiming is no two processes can get the resource at the same time. And furthermore, processes get requests in the order of the requests. The order is the lexicographic order that we are imposing. The order that we are imposing on the scalar timestamps. So the discussion is, if a process is getting a resource, then there are two possibilities. What is the possibility? It has seen requests by all other processes. It has not seen the request of some set of processes, but it has seen messages that precede them. So let's go into detail of what exactly these mean, right? So we are now trying to get into the depths of the proof, and this is the last slide. So let us now go into the details of the proof. So assume we have two processes I and j, and they are accessing the resource at the same time. So this of course is not possible, but let us assume to the contrary that it has indeed happened. So we are talking of two processes I and j, and let the requests that led to this simultaneous access have timestamps ti and tj respectively. So with no loss of generality, let us assume that ti is less than tj, which means that we break the tie by the process id. Right? So even if the Lamport clocks are the same, we break the tie by the process id. But regardless of how we do it, the important point is we have a way of totally ordering the tuples, which is a Lamport clock timestamp comma process id. We do that, and it turns out that ti is less than tj with no loss of generality. So what would have happened? This means that J must have gotten a message from I with a timestamp greater than Tj before acquiring the resource. Otherwise, by the second condition, J could not have acquired the resource. So it must have sent the messages, etc. All of that would have happened, but then I must have sent it a message with a timestamp which is greater than Tj. If that is the case, then what about the original request, right, that I actually sent? So what is happening? J is sending a message with a timestamp Tj. I is sending a message back with timestamp, let's say Tx. And we know that this relationship holds. Otherwise, J could not have accessed the resource. Now, what about Ti when I sent its original message? So, this could not have been sent after this event. Otherwise, Ti would have been greater than Tx, which would have been greater than Tj, but that is not the case, right? So, then this basically means that I sent its message to J before sending this message, right? So, before that, I actually sent Ti. If I did that, then let's look at the fun part. So, let's go over here. So, what we are saying is that we are considering the moment in which J actually entered the critical section. That's what we call in programming terminology, or access the resource. This essentially means the following. It means that at some point of time, J would have sent I a message, Tj. I would have sent a message back at some point of time, let's call it Tx. For J to have accessed the resource, Tx would have been greater than Tj. Now what we are arguing is that the original message which I sent to J could not have been after sending this message, because otherwise I would have had a greater timestamp which would have been greater than Tx is greater than Tj. But we know that this relationship is not true, because we know that this holds by your assumption. Hence it means that I would have sent a message to J prior to sending this message, which is Ti, which contains its request. This further means that when J took the decision to actually acquire the resource, it would have had the message from I. So this is an important thing, let me repeat, bear this in mind. The moment that J took the decision to acquire the resource, it is guaranteed that it would have had the message from I. And given that I and J are accessing it currently, this message would not have been released. Now the question arises, why did J access the resource? It was not supposed to. Because, so let me write it. Right? It was not supposed to access the resource. The reason is that in its queue, the request from itself was not the earliest request. There was already a request from I, and that was the earliest request. Consequently, J should not have accessed the resource. Right? Hence, what we observe is there is a contradiction. So, our assumption that two requests are they have actually acquired the resource at the same point of time, this is not correct. This has led to a contradiction. So, this is not possible. And given the fact that a wrong thing is not possible, the right thing would be holding all the time, which means that mutual exclusion actually holds. Alright. So, this is what it means, that mutual exclusion holds and the algorithm is correct. So, what did we do in this Lamport's algorithm? We sent 3 times n-1 messages, and for sure without assuming clock synchrony or bounded network delay, mutual exclusion is guaranteed. Alright. And the reason it is guaranteed is because of the way that we constructed our Lamport clocks. Right. So the key point over here that I am trying to make is that given the fact that we said J has to wait for a message greater than its timestamp from I would have sent its request message prior to that. Given the FIFO channel property that would be there in J's request queue, right? So you might want to hear this part of the video again. The message would be there in J's request queue. So there is no way on earth that J could have accessed the resource without I releasing it. So concurrent access is not possible. Consequently, mutual exclusion is guaranteed. So what we will do in the next lecture is look at many more algorithms that reduce the number of messages that are required to guarantee mutual exclusion. So the original paper on time, clocks and ordering of events was a seminal paper in distributed systems, pretty much something that started the field. This was published in 1978. You can read up this paper. So this will give you a lot of insights and understanding about the original ideas that came to define the field.